Hey everybody. All right, this is the increasing and decreasing function portion of 4.2. Okay, some of this we've already done in class, but I'm just going to go start from the beginning here. Example 4. What interval is the function decreasing, increasing, and constant? Well, if you look at this function right here, it is clearly decreasing on 1 to 3. And then it's constant from 3 to 5. And then it is increasing from, 5 to 7. I hope that makes sense. All right, let's look at example 5. What is the value of the derivative when the function is decreasing, increasing, or constant? Okay, well, when the function is decreasing right through here, what kind of derivative do you have? What kind of slope do you have? You have a negative slope. So the derivative is negative when the function is decreasing. The derivative is equal to 0 through here. The slope is equal to 0 when the function is constant. And then, of course, from here up to here, from 5 to 7, the derivative is positive and the function is increasing. Well, that holds every time. If the function is increasing, then the derivative is positive. If the function is decreasing, then the derivative is negative. If the function is constant, then the derivative is equal to 0. That information is summed up for you right here, and it's on your notes as well. It says the exact same thing that we just showed using that graph. All right, so let's look at the next thing. Guidelines for finding intervals on which a function is increasing or decreasing. The first thing you need to do is, I guess, you need to verify, if you're not sure already, that you have a continuous function. So you need a continuous function. You find the critical points of the function, and then you create a sign chart. We're going to talk about how to do this on the next slide. The sign chart tells you whether your function is increasing or decreasing. And then you determine the sign of the derivative at one test value in each interval by labeling your sign chart. You use the sign of the derivative to determine whether or not the function is increasing or decreasing. And make sure you realize this as you're making sign charts. Your sign chart is not enough to justify your response. So on my test and on the AP exam, you are not allowed to just use a sign chart and have that be the reason that the function is increasing or decreasing. You have to actually say in words the function is increasing or decreasing on the interval since the derivative is greater than 0 or the derivative is less than 0 or something along those lines. Okay, so let's look at the first example here. Find the intervals on which x cubed minus 12x minus 5 is increasing or decreasing. Is this the same example that you have on your paper? Because I'm going to change this. Mine says, I believe that I have on my paper is the same thing you have. 4x cubed minus 15x squared minus 18x plus 7. So let's use that instead, because I think it's the one that you have. Okay, so the first thing we need to do is to find the critical points. And we find the critical points by finding the derivative and seeing where it's equal to 0 and where it is undefined. So to find the critical points, we do the derivative. Don't know why I didn't write that. There we go. And we get 12x squared minus 30x minus 18. Now we need to set that equal to 0. And solve for our zeros. Now let's see, what can I divide through by? It looks like I could divide through by 6. I could essentially factor out a 6. If I did that, I would have 2x squared minus 5x minus 3 equals 0. And then you can divide both sides by that 6, and it in effect just goes away because you've canceled it. Now let's factor this. All right, so we've got 2x, x, and I think we're going to have a 3 and a 1, and that one's going to be negative, and that one's going to be positive. Does that work? 2 times 3 is negative 6. Yeah, that works. Okay, and so let's finish and get our points here. So we get 2x plus 1 equals 0, so x equals negative 1/2. And then over here we get x equals to 3. All right, so one way to do a sign chart is to use these factors right here, okay, to use the 2x plus 1 and the x minus 3. All right, so you draw a sign chart and you label it. This is the derivative. We are going to plug values into the derivative equation, so you need to make sure that you label it with the f prime. Okay, then we put our zeros that we found. So we found x is equal to negative 1/2, and x is equal to 3. Okay, so here's our negative 1/2, and here's our 3. Now, the factors that we pulled out were 2x plus 1 and x minus 3. I'm going to write those over here, 2x plus 1 and x minus 3. All right. When you plug any number bigger than 3, I'm on here, I'm in this part of the chart right here. When you plug any number bigger than 3 into x minus 3, you get a positive number, right? Agree? Okay. When you plug any number between negative 1/2 and 3, let's say 0. It doesn't really matter what number you pick. Pick an easy one because they're all going to be the same. Between negative 1/2 and 3, let's pick 0. If we plug 0 in right here, we get negative numbers, right? Now, if we plug any number less than negative 1/2 into this, we still get negative numbers. Okay, let's look at 2x plus 1. 2x plus 1, if you plug a big number, anything greater than 3 into there, you get positive numbers. I'm going to put some positives right here. When you plug a number between negative 1/2 and 3 into 2x plus 1, say 0, you still get a positive number. I'm going to put positives along here. There's different ways of writing this. I like to do it this way because I like to see my positives and my negatives. And then if you plug a number less than negative 1/2 in, you end up with a negative number. If you don't believe me, go try it. Okay, now go back to how we factored this. We had the factor of 2x plus 1 times the factor of x minus 3 equals 0. So we're multiplying them together. Okay, in order to see the sign of what we're doing, we need to multiply our signs together. If you multiply a negative and a negative, what do you get right there? Negative times a negative. That gives you a positive, right? If you multiply a positive and a negative, you get a negative. If you multiply a positive and a positive, you get a positive. Okay, that information right there tells us where the derivative is positive or negative, and that tells us where the derivative is increasing or decreasing. So to sum up this problem, I would say f is increasing on negative infinity to negative 1/2 together with 3 to infinity. Since the derivative is greater than 0 and f is decreasing on negative 1/2 to 3, since the derivative is less than 0. I hope that makes sense. If it doesn't, go back and watch the problem again, but I'm going to do another example right now. Okay. Example 7. This is the same thing you have, yes. All right, so x squared minus 9 to the 2/3 power. First thing we need to do are find the critical points, so we need to find the derivative. So the derivative is 2/3 x squared minus 9 to the negative 1/3 power times the derivative of the inside here, which is 2x. I'm going to rewrite that just a little bit. Let's see, I get the 2x times 2, so my numerator is 4x over 3 times, times x squared minus 9 to the 1/3 power. Now, remember when we're doing critical points, we need to find where the denominator, where the derivative is equal to 0 and where the derivative is undefined. Well, in the last problem, we didn't have anywhere where the derivative was undefined. It was completely continuous, but in this one, we do have a place where the derivative is undefined. So we'll look at that one in a second. Let's first talk about when the derivative is equal to 0. So f prime of x is equal to 0 when, well, if x is equal to 0, your denominator is fine. It's just a number of some sort. But your numerator is 0. So you have 0 over a number, which is perfectly legal. So your derivative is equal to 0 when x is equal to 0. Now, when is your derivative undefined? Well, f prime of x is undefined when that denominator is equal to 0. When is that denominator equal to 0? Well, that happens when x is equal to 3 or when x is equal to negative 3. Okay, so far we have 3 critical points. We have x equals 0, 3, and negative 3. Now, we need to test those on a, well, it's not really testing. We need to put those on a sign chart and determine where our function is increasing or decreasing based on when the derivative is positive or negative. I'll change colors here. All right, so this is a derivative graph, so I label it f prime. We have 3 critical numbers this time. We have negative 3, 0, and 3. All right, I'm going to do the sign chart a different way this time, and you might like this better. You might not. I don't know. This way requires a little more kind of thinking, but the other way has more steps, I guess. Okay, so let's start with on the right side. Let's start with up here. When x is anything bigger than 3. So the only rule is you can't pick the 3, you can't pick the 0, and you can't pick the negative 3. You can't pick the actual places where the zeros or the undefined happens. Just pick something in between. Okay, so let's pick something bigger than 3. What if we pick something way bigger than 3, like 1,000,000 or 100 to be more realistic? We would have 4 times 100 divided by 3 times 100 squared minus 9 to the 1/3 power. I hope you can tell from that that this is going to be positive. And yes, we do take these values and we plug them into the derivative to get the positive or negative. Now let's pick something between 0 and 3. How about 1? If you pick 1 and put it over here, you'd get 4 times 1, that's a positive number, divided by 3 over, that's going to be 1 minus 9 to the 1/3 power. That looks like the denominator is going to be negative and the numerator is going to be positive. That gives you a negative number. Now if we plug something in here between negative 3 and 0, let's plug in negative 1. Well, if we plug in negative 1 over here, we're going to get a negative over negative 1 squared is positive 1, but minus 9 gives you a negative, so we have a negative over a negative, which is a positive. Now for the anything less than negative 3, I like to think about it in really big negative numbers. I mean, if you plug in negative 1,000,000, you're going to have negative 4,000,000 on the top, and then some other positive number on the bottom because it's squared minus 9. So if it's some huge number minus 9, it is going to be a positive number, but the numerator is negative, so we are negative right here. So let's answer the question. The question was find the intervals on which the function is increasing or decreasing. All right, well, f is increasing on negative 3 to 0 and that's a union, and 3 to infinity, because the derivative is greater than 0. And f is decreasing on negative infinity to negative 3, together with 0 to 3, because the derivative is less than 0, or decreasing. All right, so summing up what we're doing here, we're looking at the function graph, the original function, and we're determining where the original function is increasing or decreasing based on the sign of the derivative. So we're taking the original function, finding the derivative, determining where that is positive or negative, and then that tells us where the function is increasing or decreasing. All right, let's look at the next example. Okay, antiderivatives. Let's see. This is not as scary as it could be, or as scary as you think it might be. We did do this one in class because y'all were already freaking out about it, asking about it. Okay. Suppose you were told that the derivative of f prime of x, the derivative is equal to 2x minus 1. What could f of x possibly be? Well, you already told me this. Thinking Sarah wasn't there that day, so Sarah, think about this. What would the original function be if the derivative is 2x minus 1? Well, the original function would be something along the lines of x squared minus x. Do you agree? Because now if we go backwards, or what we consider forwards, and took the derivative of that, we would have 2x minus 1, right? Okay, so I'm brain farting here, I'm sorry. What could f of x possibly be? Well, it would be x squared minus x, but the question is there more than one answer? Well, if our original function was something like f of x equals x squared minus x plus 4, when we went to take the derivative of that, what would have happened to the 4? Well, it would have gone away, and we wouldn't know what it is if we're just looking at the derivative. What about if it was plus 400? Well, it would have gone away, and we would not know again in the derivative what that number is. So what we're going to do when we find the antiderivative, this equation right here, when we're given the derivative and we find the antiderivative, what we need to do is we need to account for that other number that could have been there. And we're going to do that by saying plus c. And it's a capital C. I'm not sure why that matters, but it always is that I've ever seen. So it's going to be plus c. All right, let's see how that might affect things. Example 9, finding the function from the derivative is a process called antidifferentiation, or finding the antiderivative. Now this is similar but not exactly to what we keep talking about for second semester, where we use the word integration. They're almost exactly the same thing, but not precisely. So we're not at integration quite yet, but we will get there. Right now we're just doing antiderivatives. All right, let's look at example 9. Suppose the graph of f prime of x is given to the right. Draw at least 3 possible functions for f of x. Hint, if the derivative is given, then the y values of the derivative are the slopes of the original function. Okay, we're still on the, we're on f prime of x. Okay, I'm going to pause this for a second and then come back and finish antidifferentiation in a second. I'm afraid the video is getting too long though.